Every single second, trillions of bits of data are just zipping around the globe, connecting all of us, powering our entire digital world pretty much instantly. But have you ever actually stopped and wondered, how? How is that even possible? How does an email you send from Tokyo show up in New York in what feels like the blink of an eye? Well, the answer is hiding in plain sight, and also deep, deep under our oceans.
It really all boils down to this one incredible piece of technology. We're talking about a single strand of pure glass, literally thinner than one of your own hairs, that somehow carries the weight of our entire connected world. I mean, it sounds like science fiction, doesn't it? But this is the real secret behind the mind-blowing speed of the modern internet. So, just how important are these tiny glass threads? Well, get this. Over 95% of all international internet traffic travels through them. That's nearly everything. They're the true unsung heroes, the backbone of global communication, just sitting down there on the ocean floor. All right, so to really get our heads around this, we've got to start with the big idea. It's all about our world's constant, relentless need for more speed, and how we figured out a way to get it by using the fastest thing in the entire universe, light itself. The basic concept is actually beautiful in its simplicity. Old school copper cables work by pushing electricity, that's a stream of electrons, through a metal wire. Fiber optics? Totally different game. They create a highway made of light, sending super fast pulses of light, photons, through a glass tube. And those little flashes represent all the ones and zeros of our digital world. In a race, you just can't bet against the speed of light. So what does this light highway actually look like up close? To get that, we need to zoom way in and take a look at the anatomy of the cable. It's a true marvel of material science, really. Okay, so every single fiber is made of a few absolutely crucial layers. Right at the very heart of it, you have the core. This is the incredibly pure glass where the light signal actually travels. Then, wrapped around that is the cladding. Now, this is another layer of glass, but it has a slightly different recipe. And this layer, this is the secret ingredient. We'll get to why in just a second. Finally, you've got a protective plastic coating and a tough outer jacket to make sure that delicate glass stays safe from, well, everything. So how does that cladding layer actually work? How does it stop the light from just leaking out of the glass core? Well, this is where we get into the real magic of this system. It's this amazing principle of physics that makes the whole thing possible. It's a cool concept called total internal reflection. Here's the gist. When light is traveling through one material, like our glass core, and it hits the border of another material, the cladding, at a really shallow angle, it doesn't pass through. Nope. Instead, it reflects perfectly, like it just hit a flawless mirror. So what you get is this beautiful, simple process. A pulse of light gets shot down the core. When it tries to escape, it hits that cladding boundary, and bam, it reflects perfectly back inwards. Then it bounces off the other side, and so on, just zigzagging its way down the length of the fiber for miles and miles, perfectly trapped inside. This analogy right here really hits the nail on the head. It is exactly like sending light down a perfectly mirrored tunnel. If you could shrink down and stand inside, you just see this pulse of light bouncing off the walls, never escaping, traveling for as long as the tunnel lasts. That's what's happening inside every single fiber optic cable. Okay, so we've trapped light in a glass tube. Awesome. But how does that light become the video you're streaming right now, or the text message you just sent? We need to translate our data into these flashes of light. It's really this elegant three-step dance, from electricity to light and then back again. First, at the sending end, a laser transmitter takes the electronic ones and zeros from a computer and turns them into these incredibly rapid pulses of light. Think of it like Morse code. A pulse of light is a 1 and no light is a 0. Then, those pulses travel down the fiber, bouncing along, trapped by total internal reflection. And finally, at the destination, a receiver with a special sensor called a photodiode sees those light pulses and converts them perfectly back into electronic ones and zeros that the other computer can understand. But not all fiber is created equal. The heavy hitters, the cables that cross entire oceans, those are single-mode fibers. They have an impossibly thin core. And what that does is it forces the light to travel in one single, straight path. This means the signal stays incredibly clean and crisp over huge distances. On the other hand, you have multi-mode fiber. Its core is thicker, which lets light kind of bounce around more. That's perfectly fine for shorter hops like inside a data center, but it's just not going to work for connecting continents. And speaking of connecting continents, that brings us to the biggest engineering challenge of them all.
I mean, how do you send a fragile pulse of light thousands of kilometers across the bottom of the ocean without it just fizzling out?
Even light has a couple of major enemies when it comes to distance. The first one is called attenuation. You can think of it like a voice getting quieter the farther away you are. The signal just naturally fades because the glass itself absorbs a tiny bit of the light's energy. The second problem is dispersion. This is where that sharp, clean pulse of light starts to spread out and get a little blurry, making it hard for the receiver to tell a 1 from a 0.
The solution to this is just brilliant. Every 50 to 80 kilometers along an undersea cable, there's an optical amplifier. Now, here's the really clever part. These devices don't turn the light back into electricity to boost it. That would be slow and clunky. Instead, they use a special piece of fiber that's been doped with an element called erbium. A laser excites the erbium, and it adds brand new photons to the signal, boosting it directly as light. It's like a series of relay stations that keeps the light signal screaming along bright and clear across the entire ocean. So let's bring this all home. Let's look at why this technology isn't just another option, but why it's the undisputed champion that forms the absolute backbone of our modern world. I mean, just look at this. When you're talking about bandwidth, the sheer amount of data you can cram through a connection, it's not even a competition. It's not even a fair fight. A single strand of fiber can carry just astronomically more information than copper or wireless. We're talking millions of HD movies at the same time through one cable. It's insane. And the real secret, the reason why, goes all the way back to basic physics. Electrons moving through a copper wire are physical things, bumping into atoms, creating resistance, creating heat, creating interference. It's a bumpy ride. But photons, particles of light, in a super pure glass fiber, they just go. They have basically no mass, and they experience almost zero interference. It's just a fundamentally cleaner, more elegant, and way more efficient way to move information from A to B.
Now, there's a question I hear all of the time. With all the hype around 5G and super fast wireless, is fiber about to become obsolete? Are we just going to beam everything through the air?
And the answer is a really clear, simple no. The truth is, they're not rivals at all. They're partners. In fact, one absolutely cannot function without the other. Think about it this way. Every single 5G cell tower needs a massive data pipe connecting it back to the internet's main backbone. And what do you think that giant pipe is made of? You guessed it, fiber optics. All that amazing 5G speed is really just for the last wireless hop, the short distance from the tower to your phone. The real heavy lifting, the immense data hauling from that tower out to the rest of the global internet, that is all done by fiber.
So yeah, the next time you stream a movie, or you're on a video call, or you just send a photo to a friend on the other side of the planet, just take a second to think about what's really happening. Your data is being turned into these tiny, invisible flashes of light, bouncing its way through a perfectly mirrored tunnel of glass, weaving under our streets and across the vast oceans, all at, quite literally, the speed of light. It's really an incredible achievement when you think about it. We've managed to trap light in a piece of glass to build a global nervous system, a global brain. And it really just leaves you with one last amazing thought. If we can do all of this, what else can we build with the power of a single photon?